Rates of reactions are very often related to the concentration of the reactants. We can express the relationship between the rate and the concentration using something we call a rate law. All right, let's consider a reaction where we have this reactant A that just decomposes into products. All right, so the rate law for this reaction would have the form rate is equal to K times the concentration of A raised to the power of N. So let's define a few things here. K is what we call the rate constant. Okay, so this is something that we would have to determine by doing an experiment. It is dependent on temperature, right? And we'll talk more about that later. And then there's N. This is the order of the reaction. And this really tells us what the relationship is between the concentration and the rate. Order of the reaction, okay? And this is with respect to the reactant. In this case, reactant A. A common mistake that students will make is to use the stoichiometry of the reaction to identify the reaction order. So they would look at, this reaction where A decomposes into products and say that N is equal to 1 because there's only 1 mole of A, but that's not correct most of the time. Every once in a while that will work, but it's just by chance. So it's not exactly chance. We'll talk about mechanisms again in a later video. But we have to determine the order of the reaction with respect to each reactant, again, by doing an experiment. We'll talk more about how to do those types of experiments later. Right now, I want you to understand conceptually what information we can get from rate laws. And so let's talk about the significance of these orders. We'll start with N equals 0. So we call this 0th order. Okay, so in that case, if N was equal to 0, we would say that the rate is 0th order with respect to reactant A. Okay, so the rate law would become rate equal to K, the rate constant, right? Because A raised to the power of 0 is just 1. All right, so the rate would be equal to the rate constant. That means that the rate of this reaction isn't at all related to the concentration of the reactant. Let's plot this. Let's look at a plot of let's see, concentration. So I'll put a concentration versus time. Okay, for a 0th order reaction, what we're going to see is that the concentration of A is going to decrease linearly over time. It doesn't really matter how much A there is at any given point, the rate is going to be constant, and so we're going to see a constant decrease in the concentration of A. Okay. If we plotted the rate of the reaction versus the concentration of A, we would find that we have a straight line. Okay, no slope. Again, because the rate of that reaction doesn't depend on the concentration of A. It doesn't matter what the concentration of A is, as long as it's greater than 0, the rate of the reaction is going to be the same. Okay, what if the order is 1? Let me do N equal to 1. We call this a first order reaction, and specifically it'd be first order with respect to A. In this case, the rate law would be rate is equal to K times A raised to the power of 1, right? And, we're lazy, so we leave off the 1, so we just do, that would be our rate law. Well, that means that there's a linear relationship, a direct relationship between the concentration of A and the rate of the reaction, okay? So if we look at this plot of concentration versus time, what we're going to see is that as time goes on, as the reaction proceeds, the concentration of A is going to decrease, right? But it's going to start to decrease more quickly the less we have, right? Because and we can see this mathematical relationship here, because the smaller this concentration is, the slower the rate is going to be, right? So as we run out, we're going to run out more slowly, if that makes sense. Now let's look at the rate versus the concentration. Again, I see if I look at this mathematical relationship on the left, rate is equal to the rate constant times the concentration of A, there's a direct relationship. Right? And so what I'm going to see is that as the concentration of A increases, the rate of the reaction increases in a linear, with a linear relationship. Let's see, the highest order that you'll probably see in this class is second order, at least for a single reactant. Second order, okay? And so the rate law would look like this. Rate is equal to K times the concentration of A squared. So now there's a quadratic relationship between rate and concentration. So if we look at how fast the concentration decreases with time, we're going to see that that's going to end up being even slower, right, as time goes on. And then if we look at the relationship between rate and concentration, well, as the concentration of A increases, the rate of the reaction is going to increase exponentially, quadratically. Right? All right. This information is useful because now we can predict what's going to happen if we change the concentration of any given reactant in a reaction. Okay, so if we're still looking at A, decomposing into products, this is our reaction, right? Let's say that this reaction is first order. Okay, so for example, if this is first order and the rate law is rate is equal to K times the concentration of A raised to the power of 1, but we don't write the 1. What would happen if I doubled the concentration of A? What would happen to the rate of the reaction? If A is doubled, right, then the rate also doubles. Okay? All right, and you can see that if you plug in a 2 here, if you multiply that concentration by 2, then this whole right side of the equation is multiplied by 2, which means the rate is going to be multiplied by 2. All right. What do you think? So maybe pause the video here and see if you can predict what would happen if, for example, this A decomposing into products was second order in A. See if you can write the rate law first. The rate is equal to K times the concentration of A squared. What would happen if I double the concentration of A? Well, now the rate would be multiplied by 2 squared, right? Because I would plug in a 2 here. That 2 would get squared. And so the rate would be multiplied by a factor of 4. So the rate would quadruple. Okay. All right, one more kind of scenario before we end the video. What if we have 2 reactants? All right, let me go down here. What if we have A and B coming together to form products? And in this example, excuse me, the reaction is first order with respect to A and second order with respect to B. First, pause the video and see if you can write the rate law. Okay, this would be the rate law then. Rate is equal to K. You always put the K, the rate constant there, times the concentration of A, raised to the power of 1, which we don't write, and then times the concentration of B squared because it's second order. Right. Okay, now I want to know what's going to happen if I double the concentration of A and I double the concentration of B. Well, let me plug the coefficients in. And you can stop the video here and try to do this on your own before you watch this part. If I double the concentration of A, I'm going to get 2 times A. If I double the concentration of B, I'm going to get 2 times B squared. Right? Okay, so that's K times 2 times the concentration of A times 2 squared is 4 times the concentration of B squared. So if I collect those factors, sorry, I get 8K times the concentration of A times the concentration of B squared. And so the rate is multiplied, in this case, by a factor of 8. All right, so the reaction is going to proceed 8 times faster if I double the concentration of both A and B. Okay, now, once again, remember those orders, they have to be determined experimentally, and we'll talk more about how to do that later.